Good morning. Map distortion. Map distortion occurs because we're trying to do something that's really not possible. That is to take the surface of a sphere and peel it off and place it accurately so that all parts are represented as they would be on the sphere on a flat piece of paper. And that just is not a realistic goal. You can't really achieve it at 100% accuracy. So there's always compromises. And map makers have come up with three that I want to discuss today that are called projections. Three projections where the surface is imagined by the map maker, the cartographer, as being peeled off and then projected, that surface projected onto this flat surface. And that projection has some basic assumptions. The most common projection that we have is the famous Mercator. The Mercator projection assumes that the Earth is going to be projected most accurately from the equator by placing a cylinder around the globe and essentially having that cylinder only touch the Earth at the equator, and then to peel the rest of the Earth back and place it onto that map in such a way that all lines of longitude and all lines of latitude are at right angles to each other all over the Earth, which we know from our study of latitude and longitude is just not accurate. We know that there's only intersections at right angles at the equator between latitude and longitude. But the Mercator projection projects accuracy around where it touches the Earth, which is at the equator and just above and below it. So the Mercator projection has accuracy and has value in that it is very useful, in a sense by chance, because the gentleman who invented it, named Mercator, came up with a way of distorting the distance between latitude going north in such a way that he was able to create a map that was useful for navigators so that they could actually draw a straight line on their map, and that straight line would mimic the same distance over a curved surface, the surface over which they were really sailing. And that was very useful. And these rhumb lines became quite useful in navigation using the Mercator projection. The second projection that we would want to talk about takes the Earth and tilts it at a right angle, takes the piece of paper and places it at the North Pole or the South Pole. And the projected Earth only touches the paper, the final map, the cartographer's end product, at the pole itself. All the area around the pole is tremendously accurate. But as you move south or north, depending on what pole you have projected onto the paper, as you move away from the pole, you get more and more and more distortion to the point where at the bottom of your map, bottom or top, away from the center, it has no real value. But this projection is very useful for the area around the poles and is used extensively today for pilots, by pilots, in traveling the shortest distances around the globe between locations. For instance, flying from New York non-stop to, say, Korea. You can use this projection to give you the shortest distance and most efficient route. So there we have two different types of projections, both with their own utilities, both with their own problems. And again, we didn't really say, but Mercator is tremendously distorted as you go north and south of the equator. The last projection, conical projection, takes our map now and turns it into a cone. And that cone gets placed wherever you want the center of your map to be. So what happens is that you essentially pretend, let's say we were going to make a conical projection where we are projecting out from the North Pole to the top of our cone. We place our cone, see if I can make a better cone here. That's probably a little bit more accurate. We place our cone back a bit over, say, the North Pole, so that the projection of the top of our cone is directly over the North Pole, and then we place that projection over the globe, and wherever the cone touches the globe in this projection, we have extremely accurate representations of the surface of the Earth on our map. But as we move, again, north and south or east and west from those touching points, we get less and less accuracy. Now, with this kind of conical projection, you can pretend that the top of your Earth is pretty much anywhere. I could make the top the equator and conically project from that position, which is why I say that we get distortion in any of the four directions. It just depends where you have placed the top of your cone. Where have you projected that point on the top of the cone to land on the center of the Earth, and there, the outside of that cone, where it touches, will vary. But if you just imagine it over the North or South Pole, it's a very easy way to represent what a conical projection does. And it allows for very accurate mapping of the middle latitudes, particularly if you project it again over the pole. You get a very accurate projection in this section of the Earth in a small area. You get an area that might be half of the United States, a third of the United States. You get some very, very good detailed distances or accurate distances over, and shapes. Because one of the goals here is to try to get the shapes of the continents and land masses to be accurate, shorelines to be accurate, distances between locations to be accurate, scale to be accurate. So not just shape, but also, is Greenland actually bigger than South America? Is Greenland, this small area here, actually bigger than South America? Which is how Mercator projection will often show it. So these are the goals in our map making. These are the three basic projections that people think about: Mercator, conical, and GNOMONIC, from the top of the pole, flat on a point, flat on a point. You could do it anywhere, this kind of projection. One point comes in contact with the globe, and that one point is extremely accurate, moving out from the center, more and more distortion. Or conical. So essentially, column of Mercator, flat of GNOMONIC, and conic of our final map projection. And with that, I will say goodbye.